Hello, today I will be doing a presentation on transition metal dichalcogenides. So, what is a TMD? TMDs are 2D atomically thin materials that are typically represented by the chemical formula Mx sub 2, where M is a transition metal in group 4 to 10, and X is a chalcogen element such as sulfur, selenium, or tellurium. Examples of said TMD materials are molybdenum disulfide and tungsten disulfide. The materials have a number of properties not limited to mechanical, thermal, and optical, which causes them to be used in sensors, optoelectronics, and photovoltaics. So, how do you grow TMD bulk crystals? There are many concepts and methods for growing TMD bulk crystals, each with their own pros and cons. One of the most popular concepts for growing TMD materials is chemical vapor deposition. While this concept has various methods, I'm going to focus on thermochemical vapor deposition. In thermochemical vapor deposition, a powdered form of the transition metal and chalcogen are used as precursors. Because they have different sublimation temperatures, they are placed on different substrates which have their own furnaces. Both chalcogen and transition metal is turned from solid to gas simultaneously. When the transition metal is turned into a gas, it gets absorbed into the substrate it was placed on, but when the chalcogen powder is turned into a gas, it is carried by a carrier gas such as helium, nitrogen, or argon, and is carried to the substrate of the absorbed transition metal. There, after addition of chalcogen and the absorbed transition metal, the crystal is formed. The pros of chemical vapor deposition is that it is cost-effective, scalable, you could easily manipulate growth location, the number of layers, the grain size, and you could manipulate dopant impurities. Different methods introduce different pros and cons, and there are several types of mechanical exfoliation, but over here I would only be talking about metal-assisted method, which uses the semi-covalent interactions between gold and the chalcogen atoms to separate the layers of the bulk crystal. Gold is placed on both sides of the TMD bulk crystal. The gold and the bulk crystal is both attached to adhesive tape. A thin layer of gold is then attached to the thermal release tape. The thermal release tape is carefully placed on and pulled away from the bulk crystal to separate the individual layers of the TMD. Then, the thermal release tape and attached golden monolayer is placed on the substrate, then separated from the gold by adding heat to the thermal release tape. The gold and the TMD monolayer is then separated through the use of etching with a potassium iodide solution. The pros of mechanical exfoliation is that it's simple, cost-effective, and you're able to get high-quality monolayers, and it's applicable to all types of van der Waals material. The cons is that it's time-consuming and non-scalable, meaning you can't easily manipulate how many you produce at any given time. What I have over here is a couple of sketches to represent the metal-assisted mechanical peeling method. In the first sketch, you see that gold is attached to thermal tape and is placed on top of the bulk crystal, and the bulk crystal is sandwiched between two smaller gold stabilizers. In the second sketch, the one on the right, you could see that when the thermal tape was pulled away from the bulk crystal, the gold brought a monolayer of the bulk crystal with it. In the final sketch, we see that the gold was separated from the thermal tape through the use of a heat plate. The only step that isn't represented by these sketches is the etching step, where the gold is separated from the monolayer through the use of potassium iodide. As previously mentioned, TMD materials are used for things such as optoelectronics. This is due to the presence of a band gap in the material. Band gaps fall under two categories: direct and indirect. In a direct band gap, the energy peak of the valence band and the bottom of the conduction band occur at the same value of momentum. Since the peak and bottom of the valence and conduction band occur at the same spot, it is easy for electrons to jump from the valence band to the conduction band, because the electrons don't need as much energy. In a indirect band gap, The energy peak of the valence band and the bottom of the conduction band occur at different values of momentum. Since the peak and the bottom of the valence band and conduction band occur at different momentums, electrons would need the assistance of a phonon to jump from the valence to conduction band. When energy is absorbed from a photon of a preferable energy level, the electrons would jump from the valence band to the conduction band. When energy is released, the electrons are exiting their excited states, going back down to the valence band, and light is emitted in the process. One of the charged conductors of a semiconductor is an electron hole. Put simply, an electron hole is a space that lacks an electron when one could exist. Because that spot has no electron, the spot has a net positive charge which allows other electrons to recombine with those holes. The upside of using a direct bandgap semiconductor is that electrons could easily pass through them. Photons could provide the energy needed for the creation of an electron hole pair in a direct bandgap semiconductor easily, because the electron doesn't need a lot of energy in order to jump from the valence to the conduction band. Recombination would be easier in a direct bandgap semiconductor because compared to the indirect bandgap semiconductor, you don't need a phonon to mediate the process.